So, well, it's not going. I must admit that it's not going to be a short talk, but I'm trying to go a little bit faster than I planned to because we are already late, like 15 minutes late. Anyway, so I'm going to talk about INET 4.0, its new features, the good news, and the migration, the bad news. It's not so bad, but anyway. Okay, my presentation is split into 3 parts. The first 2 parts are about something that I already talked about in 2015. You can access the presentation on the Summit website. And the third part is, this is a new part, and I'm going to go into detail about that part. So let me just quickly reiterate what is this revisited network node architecture. So basically, to summarize the motivation behind this change is that the current network node architecture is too rigid in certain ways. For example, applications can't really talk to many different protocols simultaneously, which is the case in real-world applications. Also, all the protocols implement their own dispatch mechanism to communicate to multiple applications and multiple protocols. And we also have problems with implementing dual stack network nodes, which contain both IPv4 and IPv6, because of the many-to-many relationship between adjacent OC layers. And also had some problems with MANET routers, where the actual routing protocol can't be replaced due to the architecture simply from an ini file parameter, which is enough motivation to come up with something for this. And this is just summarizes the complete changes. I don't want to go into all the details. Basically, we eliminated the dispatch mechanism from all the protocols and replaced it with a common message dispatcher and changed all the necessary code to work. So basically, INET has been completely ported to this new architecture. We also added row sockets so that you can access the lower layer protocols directly from your applications. For example, you can directly access IPv4 or Ethernet, or depending on your application. This slide just shows a quick overview how the new standard host looks like. And these are the dispatchers here, these blue lines between the layers. Actually, even in the network layer, there are dispatchers because there are multiple protocols communicating with each other. And this shows that the application is able to communicate even with the Ethernet interfaces directly, or to the IPv4, or to any transfer protocol. This is a simplified version, by the way, but it just shows what is the new structure for standard hosts. So basically, if you want to, or when you migrate your actual project, if you have some new protocols implemented, then you need to do a couple of things to work with the new architecture. First of all, you have to add your protocols to the list of known protocols. Basically it's a C++ registration list. And then in the initialize method of your modules, you have to register your protocol into the message dispatcher so that during runtime, the dispatcher is able to handle the packets to the intended receiver protocol. Luckily, in applications, you don't have to do anything because it just works. And if you have your own network nodes, I mean, you are using the modules in some different way than what is INET providing, then you might need to update those too because of the dispatchers. You either need to include dispatchers into your network nodes, or you might, because dispatchers are basically completely optional, you might connect the modules in simpler ways. So basically, that's the first part, which is, as I said, already covered in the 2015 presentation. But at that time, it wasn't only planned, but now it's implemented, and it has been changed. The second part is about the introduction of packet tags. This is also a iteration, so I'm just going to go quickly through it. The main motivation is cross-layer communication, and the reason for that is, for example, applications want to control various service parameters like hop limits or quality of service parameters, so which the outgoing interface should be. Also, higher layer protocols, routing protocols might need to control resource optimization parameters, for example, in sensor networks where battery is important. And this also goes in the other direction from bottom up. For example, routing protocols might need to access link quality indications. And all these requirements need to be able to communicate through the layers. The other two is not so important, so I just skip them. So basically, this is a high-level view of what is going to happen. Basically, as packets go down over the layers, they collect various request tags, and protocols will process those tags if it's up to them to do it. And in the other direction, from bottom up, they are collecting various indication tags, and it's also up to the protocols to handle those tags in any way they see fit. So what has been changed regarding this? It's a little bit more complicated than the node restructure, because we had to basically split all existing control info structures into separate reusable tags in all the message files in INET. So basically, a tag is something that focuses on a single parameterization aspect of protocols. And from this point on, packets no longer carry control infos, which is very important because that means if you have your own protocol implementation, then you have to update the code to reflect this change. Because instead of carrying control infos, they have a set of tags attached. Okay, the tags come in 3 different flavors. We have request indications and meta info tags. They go through the layers I mentioned already, that, and they are supposed to be removed when they are processed. So yeah, this is what you need to do in your class or in your protocols. If you have specific control infos created for your protocols, then you need to split those out into tags. And probably it's a good idea to reuse existing tags if possible. But if you want to create your new ones, then it's absolutely suggested. So, and of course, then you need to replace the code for the outgoing packets to, instead of attaching control infos, you need to attach tags. And also in the processing part, you need to be able to, you need to change the code. Regarding removing tags, there's another important point here, is that whenever a packet is reused, mostly in applications, but maybe in some protocols, I mean, by reuse, just reuse the actual object, then you need to remove all the tags so that you're not surprised by some behavior of some other protocol later on. And also, if a tag leaves a node, obviously all the tags are removed. And there are 2 additional points here. The first one is the dispatch protocol request tag, which is basically related to the previous part of the presentation of the network node architecture. This is actually the tag that instructs the message dispatcher to find out which protocol should process the packet next. And the second one, this packet protocol tag, is related to the third part, which I will talk about, the new packet API, is that basically protocols have to specify what kind of protocol is in a packet, because a packet in itself is just a bunch of bytes or bits, if you will. So it's in itself, it doesn't self-describing without this information. Okay. So let's get to the third part, because it's much longer than the previous 2. We redesigned the packet API in INET 4.0, and that means that basically all the protocols has been adapted to the new API. And the reason for this redesign is basically there are a number of problems with the current approach. For example, protocols must be able to easily implement these quite common operations like fragmentation, aggregation, and emulation. And we have a kind of a solution using the cPacket API from OMNeT, which is, for example, in the fragmentation case, it's kind of kludgy because we are truncating the packet length. For the aggregation case, it's actually not supported directly. You have to roll your own solution for each protocol where you want to support aggregation, because the encapsulated packet field can only encapsulate one packet, which is obviously not right for aggregation. Or emulation support requires us to process raw packets separately, so we need to have some kind of dispatch mechanism and alternative code passes to process those kind of packets, which is wrong. And there's also this point that, for example, the TCP protocol implementation implements its own support for byte count, row bytes, and object-based and mixed kind of packets and streams, which is not reusable for other protocols, and it's not even complete in terms of being able to use any kind of mixture of those representations. So this is also an important point. I would say this one is important so that packet parts do not contain non-protocol related data. What do I mean by that? So, for example, if you look at a packet in the user interface in the runtime and you open the encapsulated packets in the user interface, then you see a lot of technical data that comes from C message, like the sender module, arriver module, which is great. It's there, it's very nice, and I know that it comes from the past because it probably comes from some past event. But the actual data that is in the protocol is kind of hidden in the structure. You have to be able to figure out, okay, where's the data that I really want to look at? So we want to get rid of those things too. So basically, the new API should support easily these features. I've already talked about encapsulation, fragmentation, aggregation. We want to be able to serialize and deserialize, of course, packets. You want to have memory efficient sharing. That's a very important point to be able to scale for large networks. And emulation support, and I've talked about this. Then we want to have queuing and reassembling and reordering as a generic support, so that protocols don't have to come up with their own implementation each time they want to implement some receive queue or something like that. Okay, so we need to be able to support that. And this representation selection is an interesting thing that we want to allow the user to put up different kind of glasses to view. When you view a packet or a part of a packet, you can view it as a sequence of bytes or as a fields, as an object with the fields. So it's just different kinds of glasses, but it's still the same data. As for the representation goals, data representation, I mean, we need to be able to represent parts just by length. That's very efficient in terms of memory. So, for example, if an application wants to send 1 million bytes, then it's just 1 million bytes. And then, of course, we need the raw parts to be able to serialize and the emulation support. And a lot of protocols have optional and variant parts in the headers. We need to be able to support that directly. And of course, for fragmentation, we need the split parts and successive parts for the aggregation. And sharing and mixing different represented parts, that's very important. And then finally, we have these four flags, the 4 eyes, I call them. The immutable parts is required for safe sharing, so that you just cannot accidentally modify something which is shared among thousands of nodes, because at some point you just forget about it. So that's very important. And incorrectly received parts is for representing errors in the parts themselves, bit errors, I mean, or incomplete parts where basically a part, is just, for example, when you do emulation, you might end up with deserializing a part which is, due to fragmentation, is just a part of an object. So it's basically, this object must be able to represent that it's not a complete representation of that emulated part. An improperly represented part, that's quite often that happens in INET, that protocols do not completely implement the specification. So some data might not be properly represented after the deserialization. So the API is basically a 2-layer API. The lower layer is centered around the concept of chunks. Basically, chunks provide different representations for packet parts. Okay, they are not subclassing C packet. They are completely different class hierarchy. And chunks can be combined to form larger chunks. That's important. And can be immutable for efficient sharing. And then the higher layer API on top of that is the containers API, which is supposed to provide us packets, queues, and buffers, and use chunks for their services. And they should always try to find out the efficient representation using the chunks. They should merge and split and share and reuse chunks on demand as they see fit. So basically, the protocols would most of the time deal with the containers API, and rarely and very small places some chunks API directly. So okay, what is a chunk? Basically, a chunk is just a piece of data represented in some way, and it needs to support a very few operations. We need to be able to insert and remove at the beginning and end so that we can really represent efficiently in terms of memory the packets. And then, of course, chunks are designed for subclassing by the user, so we allow it, we actually encourage it. If you want to create your own chunks, it's possible. And then, of course, they must be able to represent the typical protocol header parts, optional variant parts, as I mentioned before, so that's not so important. So basically, the most simple one is they are used when the actual data is irrelevant. That's most likely in an application when you just want to send, I don't know, 1 billion bytes, whatever. There's two variants of those, the bit count chunk and the byte count chunk. That's not so important, or it's not so complicated. Important, but not complicated. Then we have the raw data chunks, which is mostly used for serialization. We have the bits chunk and the bytes chunk, and the bits chunk is only needed in some physical layers where you need to be bit precise. I mean, in terms of length, because the bytes chunk is also bit precise, but in length it's byte line. So these are used for emulation. And then we have the old field-based chunks, which can still be generated from the message compiler. The difference between the old packet and the new chunk, this can be seen here. It's pretty straightforward. You need to replace the packet keyword with the class keyword, and it has to extend the necessary base class. And then the byte length was replaced with the chunk length. So it's basically that simple. Here's an example how it looks like in the user interface. This is a UDP header chunk, which is an 8-byte header. Here are the fields. You can see here all the fields defined by the chunk. These are the inherited fields from the base class, which are important so that you can know that this is a complete chunk and it's corrected, properly represented, and it's immutable, that probably it's shared. And here you can see the raw data automatically displayed using the serializer, so you actually see the bytes and the bits, or as you would see it in Wireshark, for example. And then, of course, we need compound chunks so that we can build bigger chunks from smaller ones. So we have this sequence chunk, which provides basically concatenation. So you have this chunk 1 and chunk 2, and you've wrapped them into a sequence chunk, and then you have a concatenated one. And then we need a slice chunk, which provides slicing using offset and lengths. This is mostly used for fragmentation. So you have a chunk, you give 2 parameters, and then wrap it in. And then basically this is a slice of the original chunk 1. And then for backward compatibility, we need a C-packet chunk, which allows us to be compatible with protocols which still use the C-packet API. Okay, so we support backward compatibility completely. Some things that are interesting regarding the chunks, that they are trying to merge and split on demand. So they're trying to optimize the memory representation behind the scenes for you. So for example, if you send something like, for example, send something large and it goes through some fragmentation at some point at the network, it's going to be merged automatically in the chunk API if these rules, according to these rules. So for example, consecutive slice chunks are automatically merged, or this one is also interesting. There are a number of other rules. This is happening behind the scenes, so this is just for trying to give you some idea how it works. So if we want to look at the chunk API itself, it's basically starts with creating a new header. Okay, instead of calling the constructor, the new operator, you need to use the make shared standard library function so that we can use shared pointers, because that's how we share chunks between packets. And it's just I just fill some fields here, then pick the first half of the chunk, which is just a slice, and then I put the slice into the sequence, and then put the second half of it. And when I look at it, it's going to return the whole. And if I look at it as a row chunk, this is a different class. I can just put this up. then it's basically the row bytes, and then I can even restore, putting back the original class, the UDP header classes, to restore the original. Okay, this is a chunk API. Most of the time you don't peek into chunks. Most of the time you use packets and buffers and queues. So I'm going to get there. So queuing chunks. Chunk queue is basically a class which provides FIFO queuing for chunks that come in order. So basically you have the default queuing operations, as you would see, you would think, and the representation is basically one chunk, which is kind of surprising. That why is it one chunk? Then how can I put there more data? Because it automatically changes on demand. So if you put multiple parts into it, different chunks, then if it needs to represent it with a sequence chunk, then so be it. So it happens behind the scenes. So for example, if you put 3 chunks into the queue, then pop one at the other end, and that this pop operation happens to be the same size than this chunk, then you're going to get that chunk, the exact same. But if the second pop operation is something more complicated or a larger one, then the 2 chunks might automatically get merged and being represented in a proper way. So it basically allows us for the user's code to be simpler. That's the point. That's the point, so that behind the scenes there's lots of things happening, and it's kind of tricky, but the point is that the user code has to be simple and direct. So we also have buffering chunks, support for buffering chunks. Yeah, I forgot to mention that on the previous slide, this is, for example, used in applications. For example, if you receive packets from a TCP stream, you can't be guaranteed that whenever you get some data, it's a complete data. So what you do is you put the data into a chunk queue, and then you try to pop your actual object, which is a fields-based chunk. And as long as if there's not enough data, then the API will tell you that. But if there's enough data, it's going to merge automatically and provide the data. So the application becomes much more simpler. So buffering chunks. If the chunks are coming out of order, then it's somewhat more complicated. We need to be able to represent them as a continuous memory made out of regions, non-empty and empty regions. And basically there are 2 main operations. You can clear a region or some part and replace some part. And this is mostly useful for example, a TCP receive queue is actually using this, or not this one, but one of the subclasses, which is one of the reassembly buffer, which basically provides services to merge and out-of-order parts into a whole. And this is mostly useful for fragmentation. So basically the parts arrive, the chunk, one part arrives first, and then the last part arrives, and then some middle part arrives, and then arrives a part which fills the gap here. And then let's say that the last part overrides this one and fills the gap here, so the whole buffer becomes complete. So it's done for you. You don't have to worry about it. Fragmentation, implementing fragmentation is trivial, basically. The same for the reorder buffer, which forms a stream from out-of-order parts, a continuous stream. So this shows that the first chunk arrives. It arrives at the expected parts, so it's returned by the buffer. But if some data arrives which is out of order, then it's kept there until the gap is filled by some part, and then both are returned. And finally, some part arrives which overrides this one, and again, it's returned because it's at the expected position. So for example, TCP uses this buffer, but this is also important because this buffer allows for other protocols to use all kinds of representations. You don't have to worry about what kind of representation this chunk are using. It's just going to work with whatever they are using, whatever they are represented with. So yeah, we are finally here at the INET packet. So INET is going to provide a new packet class in the INET namespace, extending the original C packet so that other tools are still working with it. And also for backward compatibility so that our INET packet can still be encapsulated in C packets. In the other direction, we use the C packet chunk, as I mentioned before. So the standard operation, there's no magic in here. It's also again represented with one single chunk, which is automatically kept in the simplest shape. Another important thing about packets is packet partitioning. The INET packet provides this header, data, and trailer partitioning for the receivers, so that as receivers process the data in the packet, the actual data is not removed from the packet. So basically what happens is that during the processing, the pointers are updated, that points where are we at the current processing, and it actually doesn't affect the packet data. So if the data is shared among different packets, then you can safely do this. Yes, in the past, INET used to contain a lot of dispatch mechanisms based on the actual C++ class of packets, which is no longer the case because it's always packet. You cannot dispatch on that. And you could think that you can still dispatch based on the class of the chunk, which is also cannot be used because the chunk class is always what you are actually requesting. So whenever you want to do some dispatch in your protocol, you must entirely base that dispatch on the data which is in the packet, which is the right thing to do, by the way, because that's what the protocol specification requires you to do. So I would say that this is a good thing instead of being a bad thing. Another important point is that forwarding, for example, in IPv4, if you wanted to forward the packet and change the time to live field in the packet, you would expect to simply just look at that part of the packet, peek that part in the packet and replace the data in it. But you actually can't do that because at the receiver side, the packets are immutable due to sharing. You can't just replace some part of the packet because that might be shared with thousands of other nodes. So you would override the value for the other nodes too, but luckily you are protected against that. So what you are doing here, what you can do here is that you can remove that part and change the removed part, which is either a duplicate or the mutable version of the part which was in the packet, and then put it back. Another option would be to create a new packet which contains the updated part, which is a duplicate of the received part, and the rest copied, shared with the rest. But this is the same, basically. It's the same result. So it's safe, basically. You are not going to shoot yourself into your phone. So this is a packet processing example, for example, in the 802.11 physical layer. When the physical layer already processes the physical header, then probably the POP header offset is somewhere here. And when the packet arrives at the MAC layer, 802.11 MAC layer, then something like this happens. It pops a MAC header and a MAC trailer, and it does something with the data. It's just a fake code. It's much more complicated than that, but you get the idea that the offsets are updated, and this is considered to be the data part, and this is considered to be the header part, and this is the trailer part. So the actual data in the packet is not changed. So if you later on somewhere look at the packet, either in the debugger or in the runtime, you see the whole data that was in the packet when it arrived at your node. This is similar to what happens in the Linux kernel, so they don't delete the data from the packet. It's because in the past, when the C packet was decapsulated, basically you lost the information that was in the outer packet. We don't do that anymore. So this is an example that shows how chunks are shared among the INET packets. For example, you can have two exact duplicates sharing the same chunk X, or you could have another packet which only contains a slice of that chunk, or you could have another packet which contains the whole chunk X plus some other chunks before and after. Or you could have another packet which contains a slice of it plus some chunks before and after, and all sorts of combinations. And it also shares, it's also possible to share chunks among packets and buffers and queues. So it's completely transparent in that sense, and you don't have to actually deal with it. It happens automatically. So it's not like you need to figure out what to share and what to not. It just works. Okay, so I tried to create a number of slides to show how encapsulation, fragmentation, aggregation happened in the past and how it is going to look like in the new INET 4.0 version. So in the past, basically, encapsulating with cPacket was pretty much well supported. All you needed to do is create your new packet, set some fields, and encapsulate the incoming packet and return the result, which is basically you ended up with from this object wrapped into another object, and that's it. Now with INET, what you do is you get the packet, you create two parts, two chunks, the MAC header and MAC trailer, set some fields, and insert the two headers. And you can, for example, in this example, you could start with a packet which contains one chunk and end up with a packet which contains a sequence chunk containing the original chunk plus the headers and the trailer. So it's pretty simple. In this case, there's not really an important difference. I mean, it was the original code, the encapsulation, it was the original code, this was totally okay. So if you look at the example in the runtime, I intentionally use the view where you don't see all the fields, because then I wouldn't be able to fit it on the screen. So what you see is basically the encapsulated packets here. This is the original INET 3.x version, and this is the new version. So basically the same packet contains a sequence chunk, and it contains a physical MAC header, snap header, IPv header, for header, UDP header, and the application packet, and then the MAC trailer. So this is much more closer to what you would see in Wireshark, for example. And you could, of course, in other view, open these objects and see the actual data fields that are in the protocol, and you wouldn't see lots of other unrelated technical fields there, which would just make you confused. So what about fragmentation? In the INET 3.x version, we used to do fragmentation with encapsulation and set bit lengths and some offsets. So basically what we did is created a new packet, added some fragment offset field and fragment number, and then encapsulated the original frame into it here, and then finally truncated the length of the outer packet. So we basically ended up with the same structure as in the case of encapsulation, but the length of the encapsulated packet is greater than the length of the packet outside, which is kind of weird because you wouldn't think that an encapsulated packet is bigger than the one which is encapsulating it. So it's kind of misuse of that API. In INET, with the new INET packet, what you do is you create a new packet with the header, the fragment header, insert the header, and then simply pick the part from the original packet at a given offset and length. That's the data, and you just append it, and then you insert the trailer, and you will end up with a structure something like this. So you start with a packet 1, which contains one chunk, and it's going to be inside packet 2 in a slice, because that's just a slice of the original packet, and some header and some trailer. It could be much more complicated than that, and simpler also. So it entirely depends on the data and where's the offset and where's the length, because if the offset and the length accidentally points to the inner chunks starting or ending point, because this might be a sequence chunk too, so you can get all kinds of different representations. So here's an example how it looks in the runtime. So originally what we did looked like this, which is kind of really weird because it's an 802.11 MAC frame containing another 802.11 MAC frame, which is like what's going on here. And this is fragmentation. So this is the whole packet, and this is the fragment. And of course it contains a number of other fields, but this itself is kind of weird. So if you look at the INET packet right now, it looks like the first packet is also, again, contains a sequence chunk, and then here are the headers. And here's the interesting part, that the slice chunk tells me that this application chunk, which is 1998 bytes long, and it only contains so many bytes of that. And in the second fragment, in the 802.11 protocol, as you can see here, there's no snap header, IPv header, UDP header mentioned at all, because the second fragment contains the remaining part of the original packet, which is not the case in INET, in the current version, because the second fragment would still contain the whole packet encapsulated, which is again weird because it's not there actually. And still, let me say this, that these are the simple cases. I mean, there can be more complicated cases. But the point is that you get a structure that is more closely related to what you would expect to see in Wireshark. Okay, as in a real network packet trace. Now what about aggregation? well, this is a complicated one. The current INET approach for aggregation is something like that. This is actually the simplified version of the 802.11 aggregation feature, which is released right now. Of course, it's more complicated than this, but you get the idea. But I start from behind because this is really interesting that you have 2 packets here, and you end up with a lot of packets. I mean, you have to create 4 additional packets to make it work. Because of the MSDU subframe, that's the requirement. That's an extra header that the 802.11 requires for each aggregated frame. These are the packet 5 and packet 6 here. And then we need to wrap it into AMSDU because otherwise the packet class combination boom happens, which we don't want to deal with. So this is how the current implementation works. So it's kind of, again, it's kind of weird, but there's no other solution. So aggregation in the new INET version happens to be something like this. You start with a new packet, then you go through all the frames, and then you pick the data part of that frame and append them to the AMSDU, which contains 1 header as required by the standard MSDU subframe header for each aggregated frame. And of course, that header has a field that specifies the length of the following data part. And then finally, you put a MAC header into the packet. So basically, you start with this, 2 packets having 2 chunks, and you end up with something like this. And if we look at the actual runtime, so this is what you would see right now. You have this AMSDU, this is 802.11, which contains another 802.11 packet, which contains another 802.11 packet. So it's kind of weird again. And in the new INET version, you have the physical header and data header. That's the usual stuff. And then comes the MSDU here. It starts here and ends here. This byte count chunk is basically a padding that has to be there according to the standard, 2 bytes, so that it's 4 bytes aligned. And then the other frame. So this is an aggregated example, aggregated packet example. Serialization also had to be changed due to, in the INET 3.6, we serialize C packets, but now we have to serialize chunks instead. What is important here, I would stress that in the past, serializers often contained protocol logic, which was absolutely terrible to put any kind of protocol logic into serializers. So from now on, serializers simply convert to and from a row stream of bytes. Okay, that's the task that they should fill or do. The rest is implementation detail. And no recursion, that's also important. Because in the past, whenever you serialize something, it automatically serializes everything in the encapsulated packet. But now we don't do that because the chunks are independent of each other. So you only need to serialize 1 chunk and ignore the rest. You don't have to deal with that. This is how you would write a UDP header serializer. For example, you get a chunk as a parameter. You just cast it to your type and then write out the integers into the stream. And this is a guard against not serializing a packet, which actually either, so the packets are the part, the UDP header either has to contain a disabled CRC or a completed CRC. Because in INET, we have this very, very good feature that you don't have to actually compute the CRC. You can declare it to be correct, which is right and which is nice to simulate, but actually declaring a CRC correct is not sufficient to serialize it because you have not computed it. You haven't computed. And this is how you would, for example, get the actual bytes from a packet. There are many other ways to, but these are two examples. Just put up the class and peek from the start to the end. And it either involves serialization or not. It entirely depends on what's inside a packet, because it might happen that this packet might came from an emulation interface, and it's already represented as bytes, so there's nothing to be done. So it happens behind the scenes, and it gives you the right answer. So here's a complete packet serialized example. It's an ARP reply. Here you see 5 chunks. You can see the serialized data in each chunk separately too, but you can see the whole packet And all these 3 Fs is basically the preamble, because that's also a bit pattern in the physical header. Okay. So as for emulation support, basically what senders would basically do is just create a packet containing 1 bytes chunk, and that's it. And receivers doesn't have to handle the raw packets in any special way. So in the old code, we had a lot of dispatch mechanism and different handlings and doing this and that. We don't need to do that. It happens transparently. So as long as you have your headers and trailers, serializers properly implemented, you are actually supporting emulation with your protocol. And testing this emulation support is pretty simple. Using fingerprints, we can just simply replace all packets leaving network nodes with a copy containing 1 bytes chunk, containing the raw data, and we're supposed to have the same fingerprints at the end of the simulation, as long as all the serializers are working properly. That's another slide about checksum handling. I was really irritated of this, that we put a lot of INET serializers contain a lot of protocol logic. So we moved them to the protocol components instead, and we came up with this generic idea that checksums are either disabled, declared correct, declared incorrect, or computed. And we better have some parameters in the protocol module so that you can control as a user whether if you want the checksums to be computed or not, because, for example, if they are not computed, then they can't have bit errors or whatever. So you get what I see. That's not quite true, by the way. I was wrong. No, it's more complicated than that. The error representation is related to this. In the past, we had this bit error flag in the C packet, which we could use to represent bit errors in the physical layer. So we could set a bit error is true for the whole packet when there was an error. But now we can mark individual parts in the packet where is the bit error. That's very cheap. That's not expensive. But if we are willing to sacrifice some computing power, then we can replace that part with a bytes chunk and actually alter the bytes, and all the protocols still supposed to work without any error, as long as the serializers properly serialize the data. Or we can even replace the whole packet. So there are many options. There are even more options than this, but how to represent bit errors. So basically, we converted all packet definitions to chunk definitions in message files in INET, and we converted all protocols. So all protocols use the new API except HTTP and packet drill. Packet drill will also be updated, I guess. HTTP has a maintainer, and we are on the track of communicating with them to actually do the changes. What's interesting here is this mixed data representation, that by default, this mixed data representation is available for all the protocols. So if, for example, an application wants to send 1 million bytes, it can send just one chunk with 1 million bytes into a stream, but at the next moment, it can send a stream of bytes, or in the next moment, it can send a fields chunk, and it has to automatically combine in all the protocols, and you don't have to do anything for that, okay? So it's just supposed to work, so you can have all kinds of mixed data combinations, whatever you want in that sense. So it's basically, it scales very well from very detailed representation to very short representations, which scale in terms of nodes. We also refactor the applications, but that wasn't that difficult part. And yeah, it's important to mention that all the changes has been validated using the fingerprint tests. All examples and tests updated, and the fingerprint tests are passed, so we can be quite sure that it still works the same as before. So basically, if you want to migrate your protocol, what you need to do is change your packet definitions to chunks in message files. If you have any kind of payload in your packet definition, then you need to remove them, because packets are not combined that way. They are combined automatically using the chunks. And you probably need to refactor your encapsulate and decapsulate method that to, instead of dealing with C packets, you need to insert chunks and pop chunks and things like that, and do some other changes. Yeah, the immutability, that might be an important point here, that you have to take care about incoming packets. Wherever you take some data out of the packet, that's immutable by default. So if you want to use an altered version of that data, then you have to either duplicate it or remove it from the original packet so that it's not shared with other receivers. And there's also the serialization. The serializers need to be migrated. If you have serializers for your packets or headers, then you need to update those two. This is not that complicated, especially if you don't have CRC handling in your serializers. So it's easier. I think that's it. Thank you for your patience.
I think we still have time for a couple of questions. One of first questions, maybe short questions, was the bit arrows. You showed us the byte arrows, then change the byte chunk. Can we also do everything in a bit chunk and change just a single bit?
Of course you can, but you don't have to do it with a bit chunk. It's the same if you do it with a bytes chunk. The bit chunk is good if the length is bit precise. Like if you have 11 bits, that's obviously not a bytes chunk, because 11 bits is like, it's not 8, not divisible by 8.
I once had the case of someone
the bit
wanted
chunk?
to for protocols where you have like a not byte length header, but shorter or longer header, like 13 bytes, 13 bits or 7 bits. And then they wanted to flip certain bits and see if protocols are like blocked this way. So
you can flip certain bits in the bits chunk, but you can flip certain bits in the bytes chunk too.
Yeah.
I mean, you would use bits chunk if your protocol requires you to have a bit length which is not divisible by 8, which is the case for some physical layers. So that's why the API supports the bits chunk. But most of the time you wouldn't use it. You don't need it.
And about the place where we, for example, for the arrow, for the bit flipping, is it usually done like in the receiver, or can we also do it like in intermediate modules, like in the channel? Like this is a special arrow channel that flips every third bit, something like this?
You could do it there too, but I would really put it in the receiver, because that's the part where the analog representation is turned into a bit representation. So I would say that's the task of the receiver. I would say that the channel is responsible for propagating the analog representation to the receiver, but the actual reception process is part of the receiver, not the channel.
Okay, can still ask a couple of questions later. So, Joseph has a question.
So hope that maybe I missed the details because I'm jet lagging a little bit, sleeping in the middle of the talk. I remember that you mentioned about the two operations. One is the queuing and the other is buffering.
Yes.
And how about the stacking? LIFO, last in, first out.
We don't have that, but if it's pretty simple to implement, I think.
Yes.
If you want,
hopefully,
we can include it.
I think that will be supported in the 4.0, because I'm not sure
That's
you
no
remember
problem.
it. Yes.
Because the heavy lifting is done in the chunks. So basically the containers are pretty straightforward. They don't contain that much code.
Yeah, but there's one notable standard need. This stacking operation is the 801Q, the VLAN. Especially this is not encapsulation, decapsulation, but the tagging.
Okay.
Yeah, it can be stacked. So according to the standard, only just a 2 level, but optionally you can insert as many tags as possible in the middle between the payload and header. Yeah, as a stacking.
I know what you mean. Basically, you need to be able to insert an optional header into the packet at a certain point.
Yes.
Yes, that must be supported. That is actually supported.
Oh, it's supported.
Not as a separate class, but you can do this with a packet, of course. But we can do more direct support for that too.
Okay. It's just a simple stacking of the certain fields is, I think, more than enough.
Yeah.
Okay.
Other questions about INET 4 porting? Yes, we have.
You've mentioned that when you decapsulate the packet, now you preserve the original header. And is it possible to make it work like the previous version, that when you decapsulate, you actually get rid of?
You can strip. There's a separate operation. It's just preserved by default.
Yeah.
So there's a separate operation to strip it, and then you can forward the packet and append or insert different headers and trailers. Of course, we need to have that.
So from your personal experience now of porting all the protocols, I know from like the past times it was usually people had their certain method of operations, how to do things. Like each time a packet came in, a simple module or a compound module, they duplicated it, deleted the received packet, and then worked on the duplicated packet. So things with the
duplicating a packet is still a cheap operation because it will actually share the whole contents, because the contents is in a chunk, and if you don't modify the contents, then why would we copy it? It's a cheap operation, but I wouldn't say that this is the way most of the protocol works. Most of the protocols works in a way that the packet comes in and you actually update the contents of the packet by inserting into headers or trailers into the packet, or if you at the receiver side you're popping parts in it from the packet and processing those parts. So you're actually updating the packet, and you just send the packet. If you need to fragment or aggregate, then you need to create your own packets, because then those packets will still share the parts with the original one, and those sharing might go very far away in the network. I mean, it might go to other nodes, and lots of things can happen, and they're still sharing. I mean, for example, if A node sends a packet out and it goes into B, and there's some fragmentation happens, and then it goes into C, and then some aggregation happens, and it goes into D. Actually, there might be a case that in the packet in D still shares some parts that with the packet in A. Do you get what I'm saying?
Yeah. The different question, if no one else has, then I can still ask one. The packet tags, you mentioned, and I read before in the porting guide that tags should all be removed when the packet leaves the actual node, computer interface card,
because that would be an
when it goes to the
out-of-bounds
channel.
communication.
Exactly, yeah. But there are packets that are actually used on the, for example, the wireless channel, but not by the user, but by OMNeT and by INET in this case, right? Or did you totally remove this? I think I read it was last year. And
okay, I see what you mean. Yeah, absolutely right. Yes, that there is. Actually, there's an extra encapsulation in the medium. We call that packet as a signal because I know what you mean. So when a packet actually enters the wireless medium, there's obviously an analog representation is needed, which can't be put into the packet, and we don't want to do that because that would be a stupid idea. So what we do is we wrap the packet into a signal, and right now the signal happens to be a C packet for certain reasons because of the tool support and such and such. It doesn't have to be, but for various reasons it should. Okay, so actually to answer your question, on the medium, yes, there are packets going, and those packets are C packet subclasses, but not of this. So you know what I mean? So there's the actual INET packet is one level deeper, because we don't want to mix the analog and all the modulation representations and things like that with the binary representation. It wouldn't make sense.
But it's most important what you also said on the slide, that developers should take care that remove all the tags when the packet accesses a certain node.
It's only important for you because you're implementing an interface. So in your interface, if you're
whenever you're implementing interface or lower layer protocols, make sure.
It only depends. If your interface is actually using some existing physical layer, then it's already done for you. But if you are creating some new physical layer, then you have to do it yourself, of course, but I guess you are reusing some existing one, so you don't have to
nowadays, before not, and that killed me the first time.
Okay.
Okay, other questions regarding the porting, maybe porting strategies, question about how you should approach your next migration.
I would say porting to the new version, there's three parts. The first part is a standard host restructure. That's basically trivial. Most of the time, you won't be affected at all. As for the tags, if you have some protocol, then pretty much you have to change your code. That's not difficult. That's pretty straightforward. You just split the control info, and it's basically a few lines of code. For the packets, if your protocol is not complicated so much like 802.11 or whatever, then it's fairly straightforward to do it. Then in this case, you have to change a little bit more code. Maybe internal utility functions will have another parameter, the header, because the header doesn't know about the owner packet. because of sharing. So if you just pass around the header, that's not enough. You don't have the packet. You have to pass both the packet and the header, because the header doesn't know the owner, because there can be more than one. So that's a little bit more complicated, but I wouldn't say that it's that difficult. So I wouldn't say that's difficult.
What is the release schedule?
One release we already have, which is a beta basically. It's the 3.99 something, no, 0, I don't know. But I don't know, it's September. It would be nice to have it for Christmas.
You can always play around in the integration branch since I think since March this year.
Yeah.
It's been pretty stable, and protocols keep coming every couple of weeks.
Yes. Yes. I think these these are the three biggest changes. These are the backward incompatible changes. So that's why. And then there are other changes too, but they are minor and they are not so important.
And it's also quite nice, the newest beta version, or the newest release candidate of OMNeT 4 instantly warns you when you try to compile the new OMNeT INET 3.99 pre-release version that you need to use a patch to support the packet structure and the packet classes, and it works quite well.
And I just one final word, that if you have any kind of feedback, we are very open to it, because we ported the whole INET, but there are other protocols outside, and you might say that, okay, for example, like Joseph said that we would need a stack or something, then okay, fine, we can put it. So this is the time to speak. If you have some ideas or some requirements or some whatever, this is the time to speak before we release the 4.0, because then it's carved into stone. No.
Just an important note is that the new INET required some changes to the message compiler too. So, but that change is not really finished, so not properly implemented. So we have a patch actually, so you can't use the INET 4 version with an released OMNeT version. You have to patch the OMNeT version first to be able to try it out. So that patch will be probably integrated into a later version of OMNeT. So probably we will see the final INET version only with the next version of OMNeT.
Yeah, it's not going to go into 5.2.
Yes. So a little bit manual work is needed.
Yes. So it's not easy to try it out. Yeah.
Okay. Any more questions at the moment? If not, then we'll give another round of applause for Andras and Levente. I think Andras will show us some INET showcases, because we talked about how to demonstrate INET features in a efficient and good way, and how to learn for new students. And they have a nice demonstration of this.
Yes, so we have realized some time ago that probably a big hindrance to the INET adoption is the lack of documentation. But we didn't know for a long time, like, in which form documentation should take, what's the most cost-effective in terms of, work and return of investment, stuff like that. And last year we probably figured out that we'll make tutorials and showcase examples. And we promised a lot of showcases and the tutorials, and now I just want to show that we have delivered some. So if you go to the main INET website, just want to show how to get here. Back to, okay, anyway. So this is a standard INET website, and you find two menu items here. showcases and tutorials. So if you look at tutorials, right now we have two groups of tutorials, visualization showcases and wireless showcases. And like each of them is like a tiny simulation study. So it's one web page. It starts with a goal, and then it starts describing the model, and then it shows some simulation results or some videos captured from the model running, and it has some conclusions. And you can download the net files and INI files and so on. So they're pretty much self-contained, and they focus on just one aspect of some simulation model or some phenomena. For example, 8.11 throughput. It says, okay, goals is to analyze application level throughput, and okay, describes the model and describes simulation results. So when you run the simulation, this is what you should be able to get. And some explanations, some more explanations, further information, and done. Or rate control? Yeah, that's a good one, yes. Okay, so for example, in 8.11 there's an automatic rate control mechanism built in, which like turns the bit rate up and down depending on channel conditions. So this showcase demonstrates this feature, describes the model, describes the network. There will be a node going around some obstacle. It will be an obstacle, so it blocks the signals, and the signal quality is just varying constantly. And you see the two nodes going around. Let's check this one. It also like shows the signal loss. Whatever, and then if we have no rate control, yeah, then in the middle when there is an obstacle is blocking the signal, then there is no reception. There's no data going through. And when we have automatic rate control, then rate control like choose another bit rate, and some data still goes through. So yeah, another chart. Conclusion discussion. So I think that these showcases can be good for like figuring out how to implement certain things, certain aspects. Can be good for teaching, and actually many things. And the thing is that we have been working on these showcases for quite a long time. It's like 1.5 years, and we have many more showcases at various degrees of completion, like from 90% down to 50, 20%. And most of these halfway ready showcases have the simulation model programmed and running, and the charts, so the results are there. Only the like English text is missing, or not complete, incomplete, or not reviewed and stuff like that. And I just want to say that if you have some ideas for more showcases, or if you have some free capacity to maybe review these showcases and help us improve the text, because most of the text was written by students whose native language is Hungarian, of course. So yes, we could use some help in reviewing them. Yes, we have some tutorials as well. Back to INET. Okay. Tutorials. We have one tutorial released, which is the wireless tutorial.
And one hidden.
And one hidden tutorial. Yes, we have also an IPv4 configurator tutorial, which is almost ready, but it's yet unreleased. And we have a visualization tutorial as well, which is somewhere, I don't know, 50% ready.
And
Yeah.
we're planning to have other tutorials
Yes.
for routing, OMNeT routing, for example, or for Ethernet.
So if some of you are using INET for teaching or have new students, then maybe we could get into contact and cooperate so that these tutorials and showcases can be more complete, and we can collect more ideas to implement. Okay, some questions? Okay, about the technology. So these showcase actually, the text is in Markdown, so pretty much plain text files, and it's up here using GitHub pages. So you push into the repository, and what you push into the repository automatically gets reflected in the website using the GitHub pages thing. It's pretty easy. So we can accept like pull requests. We also opened an issue tracker issues here, so you can comment on them if something is not, if you have ideas how to improve them, or you find errors in them, so that we can improve it. Okay, some questions?
Actually, this is something also related with Attila's presentation yesterday. This definitely encouraged me to use the INET for teaching, but in the past I asked questions of the deployment to the tens of the pieces in the lab. Yes. So in this regard, I'm just wonder the availability of any Docker images, including everything OMNeT and INET, to be deployed in the just an image. In such a case, maybe I can ask the IT technician to install the Docker system, not worry about the installations, whatever. So every PC has once a Docker system, then I just download the Docker image and just adding it each of the tens of the computers. So I'm not sure any Docker image, including OMNeT and INET, available just in case.
Okay, Rudolf, maybe.
Yeah. So actually, the idea is good, and we can and we intend to create Docker images both from OMNeT and from OMNeT INET, because we will use it ourselves too for testing. The problem is that inside the Docker image you cannot really access the display of the machine. So at least it's not easy. So you can run command line simulations, but you can't have the Qt environment and the runtime. So it's more limited. It's not something which just a packed application, but it's just more a packed command line application or service or something like that. Obviously, there are some other technologies like these click images and things like that, which could ease the deployment of the OMNeT and INET combo, but that's a different thing that we have to. That's yes.
I just want to add that Rudolf was right that you cannot access the display trivially, but there are ways to work around that. So you can either run a VNC server inside the Docker image and then connect from the host into the VNC server and use the graphical environment that way. If you are running on Linux, you can use X forwarding over SSH, or you can just mount some X11 sockets into the container. So there are a couple of ways to make it work. None of them are the simplest, and some of them may not work everywhere, but it is possible to achieve. So we'll see maybe if we can figure something out, but it is not going to be the most easy to use.
Other questions? Maybe slight remark, the videos that you showed in the tutorial, I guess those are the ones directly recorded by OMNeT currently, right?
Mm-hmm. Yes.
So that's also, maybe not everyone noticed, but OMNeT has instant recording feature at the moment, and it works quite well if you have like presentation coming up for a conference and you want to show some nice video. Don't need to do any screen grabbing like before. You can instantly record it, and it works quite well. I think it was first introduced like 1 or 2 years ago, first version of this video recording, and it's quite mature and stable.
1 year ago, yes. It was done by Attila, so.
Kudos to Attila for having it.
record absolutely smooth videos. I mean, if it's okay for you to, for the video, in the video, that's so that the time is proportional to the real time, the simulation time, then it's absolutely smooth. So it looks nice. It's even I think it looks better than recording your desk.
Any additional questions, comments? At the moment, not for the showcases. So we're another big round of applause, I think, for the OMNeT team.